It's off. You want it off? No, I mean, let's turn it on. Okay, I'll replace the chairman. Just went out for me. So our first speaker today is Eric Maskin, who will talk for Markov Equilibrium.
Thank you. Is the sound system working? You can hear me all right in back? Well, it's very good to be here for this celebration of Jean-François, who made so many fundamental contributions to our subject. In particular, as you know, he provided the foundation for a modern approach to games of incomplete information, the formulation that he and Shmuel devised for studying games of incomplete information played by Bayesian players. But ironically, he was living proof against his own theory. His theory called for Bayesian updating, but he proved himself that this cannot be done, and here's how. Suppose that you believe that proposition X is true. In fact, suppose you believe that proposition X is true with probability 1. Then Jean-François happens to tell you that proposition X is not true. Well, then you must attach probability 0 to the proposition being true. Bayesian updating fails, at least when Jean-François is involved. So, very good theorist, not all the applications work. Today, I'd like to talk about another important direction that Jean-François contributed to, and that's the theory of stochastic games. At dinner last night, someone suggested that stochastic games have not had many applications in economics. And I was startled by that because actually they've had enormous applications in economics. If you look at the industrial organization literature, the line of work that Ariel Peka started, all of that is now based on stochastic games. If you look at macroeconomics, the Phelps-Pollock model of saving, which was developed many years ago, that whole literature is stochastic games. If you look even in bargaining theory, the so-called Coase conjecture of one-sided offer bargaining, that's a model of stochastic games as well. So there have been many, many applications. There will continue to be others in the future. The work that I want to talk about today, which is new work with Jean Tirole, attempts to devise what we hope is an appropriate equilibrium concept. Well, first, an appropriate strategy concept, and then an appropriate equilibrium concept. So the goal in a dynamic game is to first define what we call a Markov equilibrium, and I'll explain what that is. And then a Markov, we want to define Markov strategies and Markov equilibria. And the idea of a Markov strategy is that my behavior today should depend only on those aspects of the past which are payoff relevant. So if we were playing a game like this one, is this the, yeah. This is a dynamic game, and this is my player I's payoff in period T. Here, the A's refer to actions, so the subscripts are time, and the superscripts refer to the player. ST is what we'll call the state of the system in period T. If we were playing a game like that, the history of the game in time T is everything that has happened up to period T. So all of the past actions, all of the past states, plus the state in period T. We'll suppose that people move after they see the state in period T. But in fact, as this payoff function is written, only ST affects current payoffs and therefore future payoffs. So all of the other variables are irrelevant. And so a Markov strategy in this setup will depend just on ST. Well, in that example, I was giving you the payoff, the set of payoff relevant states exogenously. It was just given as part of the description of the game. But if I gave you some arbitrary game and I didn't say what the state space was, you might want to derive the state space from the underlying data. And that's the task of this paper, to show how that might be done. We want to derive the state space from the underlying game to actually, and that enables us to define what Markov strategies are. So you might ask, why should we be interested in Markov strategies? I'm not going to spend much time on the philosophy, but there are traditionally three reasons to focus on this narrower set of strategies. First, Markov strategies are the simplest behavior consistent with rationality. So Einstein said every theory should be as simple as possible, but no simpler. Markov strategies are the simplest possible strategies that rational players might still use. So we might be interested in what those are. And in particular, Markov strategies eliminate the idea of bootstrapping. So bootstrapping strategies are ones where I condition on a particular variable x only because someone else does, and he does it only because I do it. Of course, bootstrapping strategies are very interesting, and in some way they're the heart of repeated game analysis. But it's on some occasions it's interesting to see what happens if we strip away these bootstrapping equilibriums and see what's left, and that's what we're doing. Another motivation for Markov strategies is they get at the idea that that bygones are bygones. What's past and what is no longer pertinent should be forgotten about. And formally, what I have in mind is that if we have two subgames with perhaps different histories, but those games look the same going forward in the sense that they have the same strategy spaces, and people have the same preferences over those strategies, then they should be played the same way. And Markov strategies and Markov equilibrium get us that requirement. And the final thing I wanted to mention is that Markov strategies give us some nice continuity. So if you change the past a little bit, you change equilibrium behavior a little bit. That's not always true when you're looking at strategies which involve bootstrapping. There you change things a little bit and you dramatically change the behavior. But particularly for applied work, and as I said, there's an enormous I/O literature building on this kind of framework. It's very helpful to have continuous strategies. So that's another reason to focus on Markov strategies. So how do we do this? Well, actually, this is the paper I'm presenting today is really a follow-up to a paper that Jean and I did about 12 years ago. In that earlier paper, and I will review it, we looked at complete information games. Those are games where the history in period T, the actions up to but not including period T are common knowledge to the players. So I'll denote by capital H sub T the set of histories in period T. And that will allow me to rewrite the payoff function. So I started out by writing payoff functions as a function of the actions in period 1, actions in period 2, up to period capital T. But I could also write player I's payoff as a function of the history, HT, and the future actions, FTs. And I'll use both formulations depending on the circumstances. So a strategy at any time chooses an action based on the history up to that point. It'll be notationally easy to write expected payoffs as a function directly of strategies. So this is player I's expected payoff if the vector of strategies is sigma, given that history HT has already occurred. And so this in particular allows us to express subgame perfect equilibrium. It's just a configuration of strategies such that if one player deviates to sigma I hat after history HT, he doesn't gain from doing so. Now, Markov strategy is getting at the idea that we're not going to condition strategies on the entire past. And so in particular, that will mean that different histories will often be treated the same. And therefore, a natural concept to use in talking about Markov strategies is the idea of a partition. We'll partition history into different equivalence classes, and the idea is that within an equivalence class, a player will play the same for all histories in that equivalence class. So my notation for a partition is just this. So capital HT of little ht is the equivalence class of histories in the same elements of the partition as HT. And I'll be interested in coarse partitions. The idea of a Markov, strategy, as I said, is that it should depend on as little about the past as is consistent with rationality. That means that we want our partition of histories to be as coarse as possible, to treat as many different possible histories as leading to the same behavior. Probably you know what means for one partition to be coarser than another. It just means that the finer partition, for each element of the finer partition is an element of the coarser partition, and in at least one case, the inclusion, the set inclusion, is strict. Now, we want Markov strategies to be measurable with respect to the appropriate partition. We say that a strategy is measurable with respect to a partition if basically it assigns the same action, it prescribes the same behavior for any two histories in the same element of the partition. So this is getting at the Markov idea. And we say that an array of partitions, one partition for each player, is consistent if whenever players make their strategies measurable with respect to these partitions, then, in fact, player I's decision problem is the same for any two histories in the same element of the partition. So from player I's point of view, he faces the same lottery. He faces the same choice problem, whether HT has occurred or HT prime has occurred. I'm using equivalent here in the von Neumann-Morgenstern sense. So these two utility functions are von Neumann-Morgenstern equivalents. And measurability is the key concept if we have partitions for which strategies are measurable with respect to those partitions. The partitions will be consistent if measurability is an okay thing for people to do. And it's an okay thing for them to do if it doesn't matter if they play the same way after H and HT prime.
But here is utility, right?
This is expected utility, right?
So that's
I'm talking about.
So if you have, for example, is constant, then it automatically satisfies always, and it doesn't say what you want. Or you could have utility being the same in different places, and this being satisfied, even though it's not really consistent in the sense you want. It doesn't exactly capture what you want.
I think it does. This is a utility function. It's a function of your own strategy.
So if, say, utility of some player is constant, then it's automatically always satisfied.
That's fine.
If there's nothing to do with being consistent with any partition or anything.
Yeah, if it's always constant, then it's going to be consistent with the completely coarse partition. You'll behave the same way no matter what happens.
No, I may behave very differently.
Not if you're behaving in Markov fashion.
It's not written there. It's not included there. My behavior may be different. My payoff will be the same, even though my behavior is different for different histories.
No, but here I'm imposing that it's a matter of definition. Okay. So you'll see where I'm going with this. So the idea here is that a player, if other players are making their strategies measurable with respect to their partitions, and my partition is measurable, my partition is consistent, then I don't lose for making my strategy measurable with respect.
What Sergio wants to say, and I think the same, is that this notion of consistency of partitions depends on the utilities. And
it
it's not
depends.
a definition per se on the notion of consistency on the partitions. I mean, it depends. The definition depends on the
utility function. I mean, of course it does. The utility functions are part of the game.
Yeah. So two partitions would be consistent according to
for this game.
For this game.
Right.
Okay,
right.
Okay,
right.
Fine.
Yeah. You change the game, and you'll change the set of consistent partition. Right. So on this slide, I allowed for the possibility that, that different players may be making their strategies measurable with respect to different partitions. And that is a possibility. However, it's a fairly degenerate possibility. That is for most games. If we pick a game at random, we'll find that in this setting where all actions are past actions are observable, players will be conditioning on the same partition. And there's an easy way to see that. If we take two histories, HT prime, and HT prime is not in the same element of J's partition as HT, that means that J, even if he's using a strategy that's measurable with respect to his partition, may behave very differently at HT prime and HT. But if he's behaving differently, then it's likely that my decision problem will be different at HT and HT prime, and therefore HT and HT prime won't be in the same element of my partition either. So for most games, in this simple setup with observable actions, past actions are observable, all players will use the same partition. So what do we want out of a Markov partition? A Markov partition should be a maximally coarse, consistent partition. And the first result that we got in this old paper is that there will always be a unique maximally coarse consistent partition, that is a unique Markov partition. And the argument is very intuitive, because suppose there were two maximally coarse partitions, call them H naught and H double naught. What we could do is to take the finest common coarsening of those two partitions, what's called the meat of those two partitions, and observe that it is also consistent. And the reason why it's consistent can be seen in a picture like this. So here is a partition where there are 5 possible histories. 1, 2, 3, 4, 5. I've labeled 2 of them. This one is HT. This is HT prime. And in this partition, the 2 histories are in one element. The other 3 histories are in the other element. And we'll suppose that H naught is consistent. Let's suppose that H double naught is also consistent, but it divides up the histories in a different way. So these 3 are together. These 2 are separate. Now, what happens when we take the meat of those 2 partitions? We get HT star. All 5 histories are now in the same element. That's the finest common coarsening. And I claim that if we take any 2 histories, HT and HT prime, a player's decision problem will look the same after HT and HT prime. Why? Well, because HT double naught is consistent, the problem will look the same after HT and this history here. But now, moving up here, it will look the same after this history and HT prime. And so by transitivity, HT and HT prime will give rise to the same decision problem. So we have that tells us that we have a well-defined, unique, maximally coarse partition. And that allows us now to talk about equilibrium. In that earlier paper, the concept of equilibrium we were concerned about is what we called Markov perfect equilibrium, which is just a subgame perfect equilibrium in Markov strategies. And it's not hard to show that they will always exist in finite games. That's just a backward induction argument. And with the usual kind of continuity requirements, they will also exist in suitable infinite games.
When you say finite game, what is the meaning?
Finite number of actions and a finite number of periods.
So the number of periods is fixed.
Yeah.
You don't from a game by which has to some paths ending earlier than others.
You could look at that, and we have looked at that, but then you need more conditions.
Yes, but then also you might have 2 points where the continuation looks the same, which happened after different things.
That's right. So we can strengthen. So for the definition of Markov that I gave you, we're only making equivalent histories which have the same length. But you're saying we can extend that.
When the future is the same.
That's right. And those are typically called stationary strategies. So stationarity is a stronger concept than Markov, but they're very much in the same spirit. Now, what I really want to talk about today, and I should check how much time I have. I got another 15 minutes, 17 minutes. What I really want to talk about today is the extension of this analysis to incomplete information. I think given that Jean-François and Schmuel provided the foundations for games of incomplete information, it's a very appropriate goal for this conference. And today I'm just going to look at the simplest case of incomplete information, but the paper looks at more elaborate setup. So in this setup, I'll keep everything the same, except that now, before anything else happens, there's a choice by nature of players' types. So at time 0, before the game begins, each player is assigned a type. Player I is assigned a type theta I, and the thetas are chosen according to some joint probability distribution, rho bar, on the type space. And the important thing is that the theta i's are now private information. That's the incompleteness of the information. So now the only change to the payoff function is that we insert a theta. You can think of theta as a play by nature. So naturally, now a strategy will depend for player I not just on the past history by other players, but also on that player's type. And we can express expected payoffs as a function of strategies, just as we did before. The only difference is that now we have to take an expectation with respect to the other player's types, because player I doesn't know the other player's types. The concept of measurability is very similar to the observable case. There's one twist, which is that now beliefs about other players' types are important. So we decided to distinguish the two concepts of measurability by calling measurability in the incomplete information case measurability star. So a strategy is measurable star with respect to a partition and beliefs about the distribution of theta and history HT, if basically two things hold. First, as before, we want HT and HT prime to be in the same element of the partition. But we also want beliefs after HT and HT prime to be the same from player I's point of view. And if 1 and 2 hold, then measurability says that player I should play the same way after theta I and HT as he does after theta I and HT prime. So it's the natural extension of measurability, but to include measurability with respect to beliefs as well as past histories. Similarly, I'll define consistency star for
no condition that beliefs come from sigma. Those are just arbitrary beliefs for that.
Yes, when we get to equilibrium, we're going to require that the beliefs be correct, but now at the moment we don't. And the allowing for incorrect beliefs actually will be important later on. So a partition is consistent star if whenever other players make their strategies measurable star with respect to the partition and true beliefs. So the bar refers to.
I'm sorry. How do you condition on HT if you don't have the threat? I mean, related to that.
No, that's arbitrary. No, it can't.
You happy? Okay. So consistency star says that if the other players are using strategies that are measurable star with respect to their partitions and the true beliefs, then if these two conditions hold, that is HT and HT prime are in the same elements of my partition, and I have the same beliefs after HT and HT prime, then I don't lose by making my strategy measurable star as well. I have the same decision problem after HT and HT prime. So just as we did in the observable case, we can call a partition a Markov partition if it's maximally coarse among consistent star partitions, and we get the counterpart of the previous result. There will exist a unique Markov partition, but the proof is slightly different. What we do now is to look at the game for each choice of a vector of thetas. We get a game of perfect observability. We're back to the earlier paper. And for each of those games, the previous result tells us that there will be a Markov partition for that game. So let's call that Markov partition H theta. And now let's take the coarsest common refinement. This is sometimes called the join. Let's take the coarsest common refinement of all the complete information Markov partitions. Remember, when there's incomplete information, players don't know as much, and so their partitions are going to have to be finer than before, because they can't distinguish so many histories anymore. So we'll take the coarsest common refinement, and that turns out to be the appropriate, that turns out to be consistent star, and therefore that gives us the Markov partition, the unique Markov partition.
Now, the conditions include something that you can, for example, have commonly known that some subset of theta being commonly known, because then you just take the join over that subset. That, I guess, is hidden in the mild conditions. Suppose the big space theta separates into two commonly known components.
Yeah.
Then, so that, I guess, the mild conditions include that you don't have that case.
That's right. So what is the appropriate concept of equilibrium? Well, before we had subgame perfect equilibrium in Markov strategies. Now we'll have sequential equilibria in Markov strategies. That is, sequential equilibrium in which the strategies are measurable star with respect to the unique Markov partition and the correct beliefs. The problem with that definition, and this occupies a fair amount of the paper, is that it doesn't always exist. Even in very simple games, there may not be a Markov sequential equilibrium in this sense. And let me give you an example, a very simple example. It's a bargaining game. There are two periods. There's a buyer and there's a seller. They have a discount factor delta. The seller has one good that she wants to sell to the buyer. The seller attaches no value to the good, but the buyer attaches either high value, theta h, or low value, theta l, with respective probabilities, rho and 1 minus rho. And here's how the game works. In the first period, the seller offers the buyer a price, P1, which the buyer can accept. If he accepts, then the game is over. The seller gets P1, the buyer gets the goods, so the net payoff for the buyer is theta, whatever that happens to be, minus P1. If the buyer rejects, then we go to the second period, and the seller makes another offer, P2, and this time, if the buyer accepts, since it's one period later, the payoffs are discounted. So it's delta P2, delta times theta minus 2. If the buyer rejects again, then both players get 0. So very simple game. It turns out that there is no Markov sequential equilibrium. And let me explain why. At least there's no, this should say no, sorry, this should say unique, there is a unique sequential equilibrium. The problem is it's not a Markov equilibrium, at least if this condition holds. And let me explain what's going on here. Suppose, it might help for me to draw on the chalk over here. Suppose that in period 1, the seller chooses a price, P1, which is quite close to theta h minus epsilon. This may not be an equilibrium optimal choice, but we have to consider all possible choices because this is a sequential equilibrium. What I claim is that the buyer is cannot accept this with probability 1 if the buyer has a high value. Because if he did accept it with probability 1, then the next period the seller would certainly set the price low, because now we'll only get to the second period if the high buyer, if there's a rejection. That means that the buyer wasn't high, the buyer must be low, so that if the next period the price will be low. So if P1 is rejected, if P1 is accepted with probability 1, the price will be low next time. But that means that a high buyer should not accept this with probability 1 because he'll get a lower price if he waits till the next period. Similarly, if P1 were always rejected, then because of this condition, the buyer can predict that the price will be high next period. It's better to sell with probability 1. It's better to sell with probability rho at a high price than it is to sell with probability 1 at a low price. So the price will be high, but then the buyer will regret not having accepted P1. So the only possibility is that the buyer is randomizing. And that means that in period 2, the seller will have updated his beliefs about the buyer's type from rho initially to rho prime, and that means that the seller will be randomizing in the second period between a high price and a low price in just such a way that this equation holds. So notice that the seller's beliefs in period 2 don't depend on P1 in the first period. They only depend on this equation. Unfortunately, the probability that the seller uses has to depend on P1 in order for the buyer to be indifferent between accepting P1 and not accepting P1. So this equation says that the buyer is willing to randomize in period 1. It says that if he's a high type and he takes P1 now, his expected utility is the same if he waits for P2. So this condition guarantees that the buyer is willing to randomize. I already argued that in this subgame, the buyer is going to have to randomize. But notice that this equation can't be satisfied without x depending on P1. That is a violation of the Markov property. It's a violation of the Markov property because once period 2 has arrived, the only thing relevant are the seller's beliefs about the buyer's type. The price that was charged in the first period is not Markov relevant, and so behavior in period 2 should not depend on P1. It should only depend on rho bar. But there is no equilibrium that doesn't depend on P1.
What would be the information version of this game? What would be the Markov actual subgame perfect equilibrium of the complete information version?
The complete information version, the seller knows knows the buyer's type. If the buyer is high, he'll offer a high price in both periods, and if it's low, he'll offer a low price in both periods. But the incomplete information means that he's going to randomize. But I think I'm literally out of time. But I actually have only one slide left to talk about. That suggests that our concept of Markov equilibrium is too demanding, what we can do is relax things, have an epsilon Markov equilibrium. Epsilon Markov equilibrium is the same, except that now we don't require beliefs to be exactly correct. They're correct only up to epsilon. You see, it's the beliefs that are causing the problem. Even in a finite game, a finite number of actions, finite number of periods, Markov equilibria involve infinities because they involve beliefs which in principle can be a continuum. And there's no reason why strategies have to be continuous in beliefs. That's the technical problem, but we can solve that problem by requiring that strategies that in equilibrium beliefs are not exactly correct, they're only epsilon correct, and then take epsilon to 0. And if we do that, we get an equilibrium which still retains the Markov spirit as far as possible. That is, we won't depend, the strategies won't depend on everything in the irrelevant past, but they may have to depend on a few things in the irrelevant past just to make sure that equilibrium exists. Sorry? And the limit always exists, yeah. So the idea is we want strategies which are as simple as possible and consistent with equilibrium. So, thank you. Yeah, Sergio.
How come the sequential didn't give you this epsilon? In some sense, that's what sequential should have done. Give you the sequence of beliefs that somehow you had to do yet another perturbation on the standard sequentiality. Add this additional epsilon saying that the beliefs are within epsilon. I mean,
sequential
says that beliefs come from a limit,
yeah.
From a limit argument.
Okay.
And you have an epsilon there already, but somehow that's not
enough.
You need another epsilon.
That's right. So in sequential equilibrium, the epsilon is on actions. It's as though this is the trembling hand idea. So beliefs are correct, but the actions are actually in this case it's just the opposite. Well, there's actually that kind of
both.
You have both. So
and the beliefs are within epsilon.
But you have to have the perturbation on beliefs too, because otherwise you run into an existence problem. The question, well, the reason is that there's no reason why. So you should think in incomplete information as a Markov strategy being measurable with respect to actions. Actions are well behaved, and beliefs. Beliefs are not well behaved. They're a continuum, and
this way you can perturb beliefs a little and get a causal partition. Get them essentially the same, even though they really should.
That's right.
But they are within epsilon, make them the same.
Actually, the way that we do it formally is to look at a finite approximation of belief space. So there are only a finite number of beliefs. With a finite number of beliefs, existence is never any problem. And then you make the finite approximation better and better, and in the limit you get the equilibrium.
Exactly.
Right. Good. Yeah.
Wasn't clear what exactly the epsilon mark. So just in the example, sense of what the epsilon.
Okay, let's see if I can go back. In this example, the seller's beliefs are pinned down by this equation. But in an epsilon, Markov equilibrium, it's possible that the beliefs might be slightly above the level that satisfies this equation or slightly below. If they're slightly above, then the seller will be playing a pure strategy, will be setting the price high in the second period. If they're slightly below, the seller will be choosing the low price. The beliefs are only epsilon correct, but now there's no problem. There's no problem with strategies depending on P1 because the seller's not randomizing anymore. He's playing pure strategies, and so we don't have so the seller's behavior in period 2 doesn't depend on P1. Because his beliefs with probability, it's the distribution of his beliefs that will converge to the correct beliefs. Let's suppose, well, to take an extreme example, suppose that his beliefs could either be 1, that is, he believes it's high for sure, or 0. So in the limits, the probability that it's high, that his beliefs are high, are rho prime. So in the limit, his expected beliefs are correct.
I think it could be that you and Jean Tirole are intervening in the game and leaking a very low information signal to the second period seller about the buyer, so, in order to get it to drive his randomization.
That's right. Think of there being a sunspot or some public event which determines my beliefs. And if the sunspot is black, I have high beliefs. If it's white, I have low beliefs. And the probabilities of that sunspot are just so that in the limit they average out to rho prime.
Thank you.
Thank you.